I mean, how many times have I not taught ever?
0.
Okay.
I'm gonna be honest with you. There's been 0 times.
Yeah. Well, we did have 2 days of hidden figures of no math.
2 days.
There's still math.
This is good now. I'm starting to think that might be like a record for you for 2 days of this.
Geometry?
Are we just gonna finish
Always that.
this part? We just have to finish this unit.
Just this section.
Yes, and then we're done.
Yeah.
Finish with it.
Okay. So yesterday we talked about limits graphically, and so the limits are basically just y values. Okay. Whether the y value is defined or not, the limit is essentially just a y value. What's important is that the limit, let's say here, the limit as x approaches 3 from the left of my function here, can y'all just slide over here? Thanks. You too, Wes. So that way I don't have to do this. Yeah, thanks. That's so much better. Okay, cool. So the limit of this function as x approaches from the left, remember that's what that little negative sign up there means, on the left side of the function, so coming from the left, okay, has to equal the limit as we approach from the right. And if they equal, so this one, as we came from the left, it approached 6, and as we come in on the right side of 3, again, we're approaching that same open circle 6 there. If they equal each other, then we can say that the limit as x approaches 3 of the function does equal 3. They both have to match. They both have to be equal. And so when you think about a limit, it's super important you understand that when I come from the left side and I come from the right side, they have to match. They have to be the same value. If they aren't the same, then we get does not exist. So there's that does not exist thing. From here, from the left, it was -2. From the right, it was 3. And because they didn't match, that's when we get does not exist, okay? Which is good to know. All right, so with that understanding, a limit means you got to go from the left and the right and get the same value. Graphically, it's really, really easy. So what do we do when we don't have a graph?
You pray.
You pray. Okay. Okay, so I want to know the limit as x approaches 1 of my f function here. This is a piecewise function. Well, a limit really means, hey, what's the y value? You just plug it in, that's right. So when I look here, this is a piecewise function, and the comma, I like to think, here's your equation, 4 minus x. For the comma, I like to just put the word if in there, okay? If x is less than or equal to 1, then we use the top formula, okay? Less than or equal to 1, that would be from the left-hand side. So this top equation is the left side of 1. And the bottom equation, if x is greater than 1, so greater than 1, that's the right side.
Why is 1 equal to 1?
Well, they can't both be equal.
Yeah, I thought they would both be not.
So, well, typically it's 1 is equal and 1 is not. That's just typically how you do it, because you don't want both of them to be equal. If they were both unequal, you'd have an open circle at 1. Okay? I'll show you what the graph looks like in a second. But and so just reading this, we have x is bigger than 1, so that's the right side of 1. And here we have x is littler than 1, so that's the left side of 1. All we have to do to figure out if the y values match is plug them in. So I'm going to look at the limit as x approaches 1 from the left of my function. Which equation do I use if I'm... Yeah, that's the one from the left side is 4 minus x. And all I have to do is plug in my x value, plug in 1. So it would be 4 minus 1, and we get 3. And then the limit as x approaches 1 from the right side of my function. Which equation do we use for the right side? 4x minus x squared. Okay, and what are we plugging in for x? 1, yeah. So 4 times the 1 minus 1 squared. Let's see, that's 4 minus 1, which is 3. Do they match?
Yes.
So does the limit exist?
Yeah.
And what is it?
3.
3. Okay. Since they both match, the limit from both sides is 3. And that's maybe a good way to think about it. When it's just a plain old x approaches 1, you got to mean, does it mean both sides? Both sides. All right? You have to check both sides. Now, so what does this graph look like? First of all, 4 minus x is a line, linear function. Is it an uphill line or a downhill line? Downhill line. It's a downhill line. And so just a quick sketch of this. It's going through 4, and I know that when it hits 3. So this is the line to the left. It's like that. It equals 3. So that's 3 at 1. I know that much. And this is an upside down parabola. And so it's coming in, it's looking like that. And it has that open circle there at 3 as well. And so that's sort of what it looks like. Okay.
No, it's not confusing.
Do you see it a little bit? Do you know that I haven't done this in a while?
Can you put them in?
You can plug in piecewise functions to your calculator. Hold on, I haven't done it in years and years. So let's see, 4 minus x. Okay, wait, hold on. Parentheses, 4 minus x divided by x test is less than or equal to 1. Okay, I think that's right.
I just missed some.
Okay, so it's a test menu item. So what I'm doing when I plug in a piecewise function into your calculator, I'm creating a true-false. Graph it or nothing, or undefined is essentially what's happening. And so it's going to graph the equation 4 minus x, and what we do is divide by this x minus 1, or x is less than 1, sorry, is a true-false statement. And the way the calculator works is if it's true, it outputs a 1. And if it's false, it outputs a 0. Well, if I divide by 0, it's undefined. All right? And so that you can see will only graph to 1. Pretty cool, huh? And then so if I want to graph the second equation, 4x minus x squared divided by that x, oh, it has to be in parentheses, x, and then it's in the test menu. The test menu is blue. So test, and we want greater than 1. All right. And so it can graph both of them, which is kind of cool. All right. But we don't need to, and that's the point of limits. You don't have to graph things in order to see if the limit exists or not. Okay. But it's a nice thing to be able to do. So again here, letter G, have a piecewise function. And this is for, let's see, we want 3x minus x cubed if x is less than or equal to 1. Is that the left or the right side of 1? Left side, left of 1. And then x is greater than 1 is the right side of 1. All right, and so again, it wants to know what's the limit at 1. What do I have to do? I have to check both sides. You have to check both sides. So I want the limit as x approaches 1 from the left of g of x. So the left, I'm going to use the top equation. And what am I plugging in? What? 1. Yeah, I'm plugging in my x value of 1. All right, so my top equation, 3 times 1 minus 1 cubed. Do you need a pencil lesson?
No, I have a pen.
Okay, you writing this down? 3,
2.
2, all right. And the limit as x approaches 1 from the right of g of x, which equation do I use if I'm checking from the right side?
Bottom.
The bottom equation, yeah. So 2, plugging in the 1, that's my x value, squared, minus 1. 2, that's 1 times 2 is 2, minus 1 is 1. Ooh. Yeah, does not exist. They do not match. They are not the same, so this does not exist, okay? So what's going on with this graph? There is a jump. That is exactly the term. All right, so I'm just going to insert here 3x minus x cubed and 2x squared minus 1. Nope, I didn't want to delete that one. Delete. Okay. And so we can look at this graph, and it is exactly what you said. It's a jump. You can see the graph comes like this, and then the other curve, the parabola, it looks like that. And there's a little gap in the graph that we will talk about eventually. All right. What about the limit as x approaches -1? What's the difference? Well, -1.
You use the same equation.
Yeah, it's the same equation, right? -1 would use, because -1 is less than 1, we would use this top equation. Oh, that's just the one equation. Am I going to get a different answer if I'm using the same equation? No. So this one, I don't have to plug in 2 different places because it's just the same equation. And so it's just the top equation, 3 times -1 minus -1 cubed. Well, that's -3. What is -1 cubed?
-1.
So it's minus a -1.
+1.
So we get -2. All right. Those become positive. You do have to know this stuff. And you do have to know fractions in calculus. We will be working a lot on fractions. Okay. Because the AP test has mostly no calculator. You got to know how to simplify stuff. All right. So it's important to do the math. All right. All right, turn the page. Example 3. Evaluate the limit. So we have our f function. Hey, what does that look like?
I swear.
That's,
Oh, it's
it's
like
the,
that. It's like, yeah.
Oh, that's it. I'm trying to think of the word.
Yeah.
I can't think of the word.
Yeah, so the horizontal lines, all right? One side is -1, one side is +1. These are exactly the same. We're going to get 1 or -1. That's all it's going to give us. What's this one?
Well, you saw.
Not. What did you say the first time? Yeah.
I don't remember.
He said volcano.
You said volcano.
He said volcano? Oh, I apologize. All right.
Oh, is this the one where it's like?
1 over x squared.
Which one's gang sign?
That's just 1 over x. Yeah, so this is a volcano.
Gang.
Yeah, gang signs is 1 over x. Yeah. It's this way. Okay. All right. So we want to know the limit as x approaches 0 of f of x. Again, if I'm doing limits, I have to check both sides. So watch what happens. Limit as x approaches 0 from the left. Ooh, how do we do that? That's kind of weird, right? 0 over 0 is a problem mathematically. It's definitely undefined. Well, you know what I can do? Because I can't really plug in, I mean, we know 0 over 0 is undefined. It's totally bizarre. But we can approximate it. So just as a thought, I'm going to just, it gets infinitely close to 0. What's super close to 0 on the left-hand side? But negative, yeah? So negative, so I'm going to test like -0.001, all right? That's really close to 0. It's on the negative side. Does that make sense to you? So we can think about this kind of numerically. So I'm going to see what happens when I plug in negative 0.001 over negative 0.001. And what's the absolute value of negative 0.001?
0.00.
Oh, yeah, 0.001. And the bottom is negative 0.001. And what does that simplify to? Negative 1. Okay. Well, that's kind of interesting. So if we test the limit as x approaches 0 from the right, again, when I plug in 0, 0 over 0 is undefined. That's totally not okay. All right? And so instead I can think, hey, well, let me test something close to 0, really, really close. What do you want to test that's close to 0 on the right side? 0.001. Positive. We're on the positive side of 0. All right, so 0.001 inside absolute values over 0.001. What's the absolute value of 0.001? Still the same thing, 0.001 positive. All right, and that just reduces to 1. Do they match? Do they match or are they different?
Different.
They're totally different, which means this is does not exist. And why does it not exist? Because there's a jump. Graphically, one side to the left has a value at negative 1, and it's undefined at 0. And then on the right side, it's always a value positive 1, but it's undefined at 0. There's a big jump. They don't meet up. So it does not exist. The limit does not exist. Okay? Does that make sense to you?
Yeah.
Okay. So on this one, can x be 0? Can we plug in a 0 for x? No. X cannot be 0. That's a good thing to recognize right off the bat. We cannot plug in a 0 because 1 divided by 0 is undefined. But I do want to look at this one graphically. I've already graphed it for you. We know that this is a volcano-shaped graph. All right, it looks something like that. And that's a good thing to know. We know also, because we did pre-cal already, what happens graphically when we know x can't equal 0? Asymptote. Very good. We have a vertical asymptote right there. That is the vertical asymptote at 0. And so when I look at this graph and I think, hey, what's the limit as x approaches 0 from the left side? So we're approaching 0 from the left, which means I'm moving along the function, coming in to 0. It's going up. Where is that function going to? Positive infinity. Yeah, it absolutely can go to positive infinity. All right. And then what's the limit as x approaches 0 from the right-hand side? So from the right, we're coming in on the right side, approaching 0. We're driving along the function, and it's also going to positive infinity. Do they match?
Yeah.
They do. So there's a couple things we could say. We could say, yes, they both go in the same direction towards positive infinity. But is infinity really a number? Not really. So does not exist is also an acceptable answer because it's not really a number. We like limits to be actual numbers, but we can use infinity when they both go to the same place. It just gives us more information about what the graph does. What do we do for the limit as x approaches 1? Of our g of x function? Just plug in 1. 9 times out of 10, oh, well, in calculus class, it's more like 3 times out of 10. You can just plug it in, all right? So let's just plug in 1 to our function. So that's 1 over 1 squared, and what do we get? 1, okay? So 3 times out of 10, you can just plug in your x value. The problem occurs if we have something that's undefined, okay? We get issues. So, knowing that sometimes we can just plug things in, example 4, How do we find the limit when x equals, or when x approaches 3? Plug it in, yes, we can just plug it in. 3 times 3 squared minus 4. Now, I will tell you, in calculus, we follow your work. So it is important that you write it out fully. You're allowed to skip 2 steps, not 3. Okay? So, like, plug it in, and then you could do the square, so 9 times 3, and get 27. But you can't do the whole thing and just get your answer. Okay? So we get 23. Okay? Here again, we have a rational fractional one. So before I even start, I'm thinking to myself, hey, what is x not allowed to be?
0. -1.
-1. Why -1?
Makes the bottom 0.
It makes the denominator 0. Yeah, if I plug in -1, -1, yeah, -1 plus 1 gives me a 0. So that would not be allowed. As long as I'm not using -1, then I can just use direct substitution, all right? So I can go ahead and just substitute in my 1 squared plus 1 over 1 plus 1. What is that, 2 over 2? Which is 1.
Oh, you can do that?
Mm-hmm.
That's loud. So you're squaring 1 and then adding, but then you add to the bottom. Oh, that sounds like you that.
All right. And again here, cosine, if you think about the cosine curve, what's the cosine song? High, middle, low, middle, high. Okay. So the cosine curve is a real nice smooth curve. And because it's not going to have any weird asymptotes, we can just plug in. So again, we're just plugging in 2 times pi over 3. What is 2 times pi over 3?
2 pi.
2 pi over 3. Ooh, 2 pi over 3, 1 pi over 3, 2 pi over 3 is right there.
That's gotta be 1, right? Negative.
-1/2. Very good. -1/2. I'm glad you haven't forgotten your trig yet. Okay. Yeah, the cosine value is the x-coordinate. That's a negative land. That's a little shorty leg there. All right, -1/2. Okay, questions on that? So sometimes, oh, that's it. You can just plug in some. Okay? All right, you're on the same Delta Math as yesterday.